Good afternoon. So today we will discuss two techniques, that is mainly to the small angle scattering technique, that is small angle X-ray scattering and small angle neutron scattering, and little bit about basics of microscopy. So far we have discussed mainly technique X-ray based diffraction techniques and neutron diffraction techniques. So today we'll see the scattering techniques. That the basic difference is that in case of earlier that diffraction study, that X-ray and neutron diffraction that we have studied, there your angle is more than high wide angle. You can say here you will show that small angle scattering techniques here. Okay. So why we need a scattering pattern first of all? So if you see the the size, the size ranging from 10 nanometer to 0.001 or up to angstrom level, you can see there is a molecules of micelles, nanoparticles. They are order of very small size or microscopic length scale. And if you go to bacteria, grain boundaries, those you will get in microscopic length scale. If you see the X-ray diffraction, what we have studied, so that mainly shows, that D-spacing, in the range of about, in this range of below 1 nanometer or so. So beyond that, if you see that in the region of 1 micron to 1 mm, so those can be seen by optical microscope, light scattering technique, as well as electron microscopic technique. But if you want to show something between 1 nanometer to 100 nanometer or 200 nanometer in the range of that, so there we need the scattering technique, that is small angle X-ray scattering and neutron scattering. So mostly to see the size of nanoparticles, size of micelles, carbon nanotubes, these polymeric aggregates, or some protein structures. So those things you will able to see by using this, scattering techniques. So X-ray and neutron measurement can't produce picture of the particle. Like in electron microscope, there we used to get the picture of the particular image we used to get. But in X-ray and neutron, that can't produce a picture. So that's why we are using mainly scattering to see the size. So if you see the advantages of this scattering technique, so they are very fast, and it has a meaningful global average instead of just local information. Instead of giving a local information, you will get a broader in picture of the system, and it can prove the buried 3D structure instead of surface projection. Like if you see this TA microscope, so there we are able to see the surface structure. But here, if you see this diffraction rings, and then you can able to see this, what are the information buried in this side, the 3D structure. So those information you can find out, and it's an in situ and non-destructive techniques, and can prove in liquid state during transformation, like some phase changes is happening, or is some function inside somehow what are the functional devices. So those information you can able to get in liquid state. And the main disadvantage of this new scattering technique, if you go for X-ray or neutron, the difficulties lies in its interpretation of data. So you need a proper model to fit your data, and then to find out that interpretation of results, that will be quite difficult. So if you see the comparison of small angle X-ray scattering and microscopic technique, you can see the microscopy uses lenses to reserve the real space image to the sample of the sample. You can see you have a sample here, and then incident beam is falling, and you can focus by using a lens, and you're able to get this real space image. But in case of SAS, that measure interference of wave vectors. So when you have an incident beam falling on the sample, whatever the scattering is happening, so that scattering going to the detector, and it's creating an interference of wave. So then you have to go for a Fourier transformation, and then it will to average out over a specific volume to find out that your particular information. So these techniques is mainly used characterizing of nanoparticles, probing interaction among molecules. Like if you have 2 or 3 molecules how they interact to each other when they come closer. So those information we can able to get by the scattering technique, because this is the web vector from one particle to the nearest neighbor, so they will interfere and you will get a interference wave that you can analyze that to get a information about the shape of the nanoparticle, size of the nanoparticle, and then studying the structure of self-assembled nanostructures, and you can even analyze the multi-component systems. So if you see the small angle neutron scattering, so neutron X-ray scattering technique are powerful tool to study the structure as well as the dynamic information of the system over a wide range of lengths. You can see the 1 to 100 nanometer, and in different time scale you can able to see. As I discussed earlier, the neutron scattering, mainly scattering due to nuclear interaction, and being neutron is a magnetic component, we will also have magnetic interaction due to unpaired electrons in the system. And then in case of X-ray scattering, the scattering is only from electrons. If you have a high-jet material, that we have discussed how that scattering intensity is much higher in case of high-jet material. So if you see that small angle X-ray scattering mainly uses that X-ray, that is the electromagnetic radiation. It's mainly depend upon this electron density. Whereas if you go for a neutron scattering technique, so that uses a neutron particles, and here instead of electron density, you have a dependent on scattering length density, and this scattering length density randomly vary from across the periodic table. So whereas electron density is varies with the increases with the increasing atomic number. If you see here, then X-ray, what you see, you can see the tree, and you can see the bone images, that bone structure that you will able to see by the X-ray, because high dense material, so high density material, so those will be opaque, that less transparent, the X-rays will be there, so you'll able to create shadow image of that. In case of you can say it as a bone structure, you can able to see, but if you go to neutron scattering, you can able to see the bones as well as the leaves. That means you can also see the tissue information. That's why the bone plus leaf both can be possible. So neutron can locate even low jet element very easily, like hydrogen, carbon, deuterium. So all those low jet material you can get by using the neutron scattering technique. So by combining these two techniques, so X-ray and neutron, they're complementary techniques. So if you do both neutron and X-ray combinedly on your sample, you will be able to see the both, the information from X-ray, like hard material, as well as from the neutron of the soft material. So both can be obtained, and you could be able to get better information based on both the techniques. Okay, so if you come into the history of small angle X-ray scattering, and this method was first introduced in 1930 by Andre Goiner, and throughout 1938 to 1950, the Goiner and other developed, various fundamentals were developed, and then the first experiments were performed in around 1950s, and the usage of SOX increased. The more user friendly it become after that, beam lines that adapted the method, like in synchrotron radiation, all those sources, after the beam lines come into the picture. So the small angle X-ray scattering or the neutron scattering experiments was more user friendly. In mid 90s, the number of such publication, if you see, so that has been increases. So what we can measure by using this technique, if you see, that you can measure size of the scatterer, like if you have a nanoparticle, or if you have vesicles, or if you have micelles, so that's the scatterer, those are the material so which scatter this X-rays or neutrons. You can able to measure the size of the particles, and also amount of scatter, how much intensity is of the light that X-ray is getting or neutron is getting scattered. So that can be measured. In addition, you can also see the polydispersity of the nanoparticles or polydispersity in your micelles or vesicles, how it's formed. It's especially in vesicle as well as in nanoparticles, and distribution. That distribution you can able to see. And in addition, you can also get information about shape of the nanoparticles, the shape of the materials which you are exposing under X-ray or neutrons, and also composition of the scatter can also be possible. So you'll able to see intensity versus Q, that in case of normal, the conventional X-ray diffraction techniques or X-ray diffraction technique, we use 2 theta that express in theta. But here we are expressing in the terminology of Q. That Q is nothing but is a wave vector, is a scattering vector. So if you see that this is a sample, here the sample surface, then incident wave that beam is coming here, and that incident beam is falling on the sample surface, and then you can see that the straight line, and then see the scattering here, that is the angle of 2 theta. So here if K incident wave vector is K, and this K dash is the scattered one, then you will Q, that Q wave vector will be K prime minus K. So this Q is nothing but 4 pi by lambda sine theta. So it's all related to the scattering angle theta. That scattering angle that mainly measure that the neutron or X-ray that scattered in different values of wave vector Q. So instead of angle, we express the angle is very, very small. So instead of that, we express is a wave vector. So that is mainly the intensity of the light from a particular value. So those things we are considering. So mainly it uses coherent, that in-phase elastic scattering of radiation at very small angle close to the straight through the beam. So you can see the angle here is very, very small, and that angle is from 0 to 10 degree. So it's mostly below 10 degree that used in case of small angle scattering techniques. So it's incoherent, like those are incoherent scattering which occurs here. So that will give you a background structure, whereas the coherent scattering mainly give you the information about the shape and size. If you see this wave vector K, that Q, so that is related to your D spacing D by a formula of D equal to 2 pi by Q. You can see that wave vector K can be written as a 2 pi by lambda. So you can see that this is the wave vector K, and this K prime, and this is Q. So Q equal to by 2K, if you apply the sine theta here, so 2K sine 2K S sine theta. So 2K sine theta, so that is 4 pi by lambda sine theta. And similarly, if you consider the Bragg's law, as we have already discussed, that Bragg n lambda equal to 2d sine theta. So you can express this 1 by d equal to 2 by lambda sine theta. So then you can see that if you compare these two sine theta, and then here this terminology, and then you will be able to see that d equal to 2 pi by Q. So Q is expressed in nanometer inverse, or in wave vector, or in angstrom inverse. So depending upon your, that Q, if the wave vector and d spacing is Q vector is larger, d spacing will be smaller. So they are, they're correlated by this way. So if you see the Bragg's law and distance that we discussed, that is inversely proportional to the Q. So to D is inversely proportional, is 2 pi by Q, so is inversely proportional to the Q. So here if you see that, is low Q region, low Q, that small angle region, and a high Q, that wide angle region, you can see this is a small, this is inside a crystal structure, that if you have a Bragg's law satisfied here, and then you will be able to see the, that D nanometer, you will be able to see less than 1 nanometer. But here the scattering angle is greater than 10 degrees. This is a small, this normal X-ray diffraction techniques. But if you go to Sachs or neutron scattering, is a sun study. So what there, you have a big particle, and then you have an angle is very, very small. So that means angle is less than 10 degree here. So what you are able to see here, you are seeing a larger particle, 1 nanometer, 200 nanometer. But that means the high Q, that is wide angle, you will give to the interparticle distance, that atomic level data, interparticle atomic, that is small structure, you will be able to see here inside this small information. So these are some grains, and inside that small information you are able to get. But if you go to low Q, that is small angle thing, so then you have to interparticle. From intraparticle, you will see interparticle interaction, and colloidal level data. That means you are seeing the whole structure of the particles. We're able to see. That means larger the structure, that means the smaller the scattering angle. So once you go to the larger structure, you very low angle, you scattered it here from the bottom. So then you'll able to see that, the shape and size of the particles. So that we'll discuss individually. So if you see the importance of small angle techniques, so you can see here you have a D equal to 10 angstrom, your Q equal to 0.6, about 6 angstrom inverse. And if you see 100 angstrom, it's about 0.06. When you go to micron size, all these things that, see the Q web vector Q, that is very, very small. So that means, so we are mainly dealing with this Q range, that small angle 0.1 to 10 degree. So where the Q lies in the range of 0.001 to 1 angstrom. So here the angle as well as the wavelength, that lambda equal to 1 to 10 angstrom, that these two is mainly important parameter in case of small angle scattering studies. So high angle X-ray scattering usually 10 to 160 degrees centigrade. The atomic scale that I discussed, that you will get mainly d-spacing information, atomic structure information you will be able to get. That is the, inside this nanoparticle, how the planes are arranged. So those interplanar distance, that you will be able to find out by using this atomic information, by using high angle X-ray scattering. But you go to small angle X-ray scattering, so you'll be able to see the whole things, because here the diffraction beam is coming like this. But if you see that whole nanoparticle, that there the diffraction is mainly from here. So on the from top surface, the surface of the nanoparticle. So you'll be able to get that, big structure that you'll be able to get. So if you see the information that you get, so it's mainly the neutron and X-ray wavelength are almost equivalent to the space between the atoms and the crystals. In the atoms, that if you see that whatever the lattice spacing is there, so that the wavelength is in the range of this. That means that X-rays can be used as a, like the X-ray diffraction, neutron diffraction, to see the information about lattice spacing. But that gives the diffraction peaks at high angle correspond to atomic position that we discussed. But if a large structure, that small angle, what you see, we are able to see the, small big particles, mainly fiber size, polymers, surfactants, dispersion information, nanoparticle, liquid crystal, biological material, virus, bacteria, all those sizes can be measured by using this small angle X-ray technique. So that means in XRD, we are using this area, this region that fix that atomic structure information we get. But in case of small angle neutron scattering as such, so 1 to 100 nanometer, so there we get the large structure. So here the two things we will able to get, that nanoparticle shape and size, and then form of particular size of the particle, that information, that depending upon the interparticle interaction or intraparticle interaction, we'll able to see how the structure factor, form factor varies, and then we'll able to get the information about both dynamic as well as shape information. So the diffusion, that experimental part of the small angle X-ray techniques, those has instrument, conceptually very simple. That means you have a source here, and then from the source you have a monochromator that will mainly separate the different wavelength and only allow that single wavelength. And after collimated, you'll be able to get parallel beams, and finally it fall on the sample where it scatter and it's come to the detector. So the detector mainly used here are 2D detector, that's means the charge coupled detector, CCD detectors mostly used here. So source, you have an X-ray generator, and that you can use a synchrotron radiation for X-ray, and for the neutron, we have to use this. For neutron, you have to use a spallation source of the nuclear reactor source, and monochromatic that defines wavelengths, which allows only particular wavelength, and you have a collimation optics that I told, that you have a divergence where parallel beams will be determine the maximize the size probe, and finally it falls on the detector, this detector, and that detector is a the 2D or charge coupled detector, so it provides better angular coverage. So distance from the sample to the detector that we have determined the size range measure. So varying the distance here, this distance and distance to the sample to the detector. So that will determine the size, particular size you can able to measure by this technique. But here, as I told, that instead of the theta or 2 theta, the peak position, here we measure that intensity that is generally expressed by di by d omega. So that is a scattered intensity angle, a solid angle. Like you have an incident ray I is falling on the sample substrate, then here the scattering is occurring. So you are measuring the solid angle, that particular angle here, the d psi, di by d psi, d omega. So that is the that scattered intensity at a particular solid angle. So here in a particular unit volume, a particular volume that we are measuring. So intensity I di by d psi are falling on the sample, then I0 is the primary intensity, and T is the thickness of the light transmitting the material, T is the transmission, and D the thickness. So you have a scattering cross section for unit volume, that is d epsilon by t omega. So that we measure that scattering cross sections. So SANS instrument more commonly provided reduced data in absolute unit, that's 1 by centimeter, than the SAX instrument. So that means what we measure here, that mainly the scattering cross section per unit volume. For a particular volume, how much scattering is occurring, that we call the scattering cross section per unit volume. So that you is to measure. So the incoming wave scatter of the electron cloud in case of X-ray, or the nuclei in case of neutron. That means you have a incident beam that is coming here. So that interact with the particular this electron cloud, that or in case of X-rays, and nucleus in case of neutron. So interference of the scattered wavelets from the material add up to next scattering amplitude. Like a particular material is here, then you have a scattered here. So you have a particular solid angle you are measuring here in a particular solid angle. So that detector that measuring the scattering intensity, that net scatter will be added up interference of scattered wavelet from different particles, and then you have to apply a Fourier transform of this to get the intensity IQ. The scattering profile can be described with the parameter of scattering intensity. So how much this scattering is from the scattering cross section of a unit volume, from that particular volume, how much scatter intensity is coming IQ. So that we measure, that is nothing but pi by 1 by v into rho r to the power e IQR. So IQ is the modulated by the interference effect between the radiation scattered by different scattering bodies. Like you have a different few scattering bodies, so the scattered from all bodies will be added up, and then you will be applying Fourier transform, will get the intensity of the magnitude of the scattered intensity. So if you see in case of real space, that all the spots will be able to see, and then after Fourier transform you'll get how the intensity IQ with respect to a vector is decreasing. So you to characterize the size D, one needs to do scattering experiment in which Q span in the range of Q equal to pi by D. So that that D if the size, then pi by D in that range where you have to see that area span range to find the value. So if you see a little larger particle, then we see how the scattering data is immediately decaying here. So IQ here, this distance. So IQ versus Q, from this plot you can able to get the larger length scale and the low Q technique. You can see the larger length scale you are getting, you are measuring a low Q technique here. So once you got that this real space image, then you can able to transform it by Fourier transform to the scattering data, and then by measuring the scattering intensity, you'll be able to see how how your particle shape and size are varying. So You see the general expression for the scattering intensity. Scattering intensity, if you see, so you can IQ is that depends upon n, that number of density of particle. Like you have a in solution or in solid, if you see Newton scattering, the number of particle is there, okay, or is this number of particles. So that is n, the number density of particle, v is volume of the particle, and rho the scattering length density of the particle, and the matrix that may be in case of medium, it may be water, or in case of in some solid sample, what is the matrix is there. So that has to like say clay particle in a cement or something. So or that can be considered as a matrix. So you have a rho IQ intensity n into rho of particles minus rho of medium to square into volume into PQ into SQ. So PQ and SQ are two factors that is coming here. That is form factor PQ, and SQ is the structure factor. So this PQ, that form factor is nothing but intraparticle interaction. That means within the particle, if there is an interaction, that is intraparticle structure, that is form factor PQ is equal to FQ square. And where PQ reflects the distribution of scattering material in the scattering particle, how the internal things are contributing to the scattering. It depends on the shape and size of the particle, that PQ. But SQ is interparticle interaction, like you have one particle here, another particle here, so how they are interacting to each other, that interparticle will give you structure factor. So PQ is equal to mostly in case of electron X-ray it's FQ square, that scattering intensity square, but SQ is 1 plus summation of IQ, that R minus the distance that you see here. So interparticle distance here related to the spatial distribution. You can see if you in this particular region is RK and RK dash, this RK minus RK prime here. So that interparticle distance that is there. That this SQ examples is mainly hard sphere, potential sticky sphere. So that gives that interparticle interaction of a hard sphere model, a hard sphere potential, sticky spheres. So those will give you interparticle interaction. Otherwise, mainly you'll get intraparticle, that intraparticular form factor here. So it's mainly upon this rho p minus rho m, that is nothing but the contrast of the particle, that we call in case of scattering technique, we call its contrast, that is scattering length of the length density of the particle minus that matrix. As I told that IQ, if you see this terminology, so V square, P, Q, and SQ, there may be an N, there you consider as a constant, and only that IQ is proportional to PQ, proportional to rho P minus rho M square. So this is called as a contrast, rho P minus rho M square, the whole square is called a contrast vector. As I told, in case of X-ray, it's determined the X-ray scattering in length, and where the neutron is the scattering length, and that the Newton scattering length. And you can see in case of X-ray how the interaction varies with atomic number. You are smaller to larger, you have a very big scattering intensity here. But in monotonous in case of jet, but it is randomly varies with the atomic number. In case of nucleus, you can see the size. In case of hydrogen, we get negative, and then some cesium again small, but zirconia that's quite high. So because of that, as I discussed here, that high angle X-ray peaks are intensity are less, but in case of neutron diffraction, we have random type of peaks. So because of this is scattering length density of depends, and the other one is mainly electron density. So if you see the scattering length density, the electron density, that one thing, and another is the scattering length density SLD of this Newton scattering, small angle Newton scattering, that is rho equal to summation of Pi by V, that is the average scattering length density. Rho of a particle is simply the sum of the scattering angle per unit volume. Scattering length per unit volume. So how much the scattering takes place from the region, that is the scattering length, that is scattering length per unit volume, you will express that rho here. So if you see the hydrogen, you can see it's expressed generally in terms of B 10 to the minus 12 centimeter is negative, whereas in deuterium just in one hydrogen one hydrogen atom extra, that is showing 0.66. So this, because of this variation, negative to positive, mostly water and D2O, that is used as a solvent for all these small angle Newton scattering studies. So the carbon and all other sulfur, you can able to see how that scattering length varies. So zero contrast means no small angle scattering. If there is a row of that is I told row particle minus row sample or that raw material, this should be very, if they both are equal or if they no change, then zero contrast, then you'll able to see no small angle scattering is possible. So you can see the example here, like you have a contrast variation, the solvent that matching technique, that matching the scatter density of the molecule with that of solvent. Like you have a making invisible to visible. Like you have a solvent is here in the green color, and in pink color you have a particle or you have a vesicles. So you can mismatch that, solvent matching. So particular solvent you take, so that what will happen, it will the contrast will differ from that of the particle, and then that you can able to study the component rendering. Another, like one component will be visible where other will be invisible. So solvent mismatch you can apply here. You can see if a core cell structure like this type of, you can see to make the core structure visible, the cell has to be, scattering length of the cell will be equivalent to that of the solvent here matrix. But in case of to see the cell structure, core has to be, scattering that of contrast of the core will be equal to that of, of the solvent. So solvent, the row green, that should be equal to row of, this core, to see, that is the core, to see the cell structure here. But in case of this row of cell should be equivalent to row of in this matrix. This is matrix, row matrix. So that means you can able to see something invisible to make visible by varying the contrast. If one example you can see here, if a glass rod, if you put inside water and in immersion oil, you can see here this is visible here, but here the glass rod is not visible. So that based on the refractive index delta Ri. It's like the contrast is similar to like that, so that we can able to see the structure of the information when you have a contrast variations. Okay. So if you see this contrast in sun is almost similar to that of this, as I discussed here. This IQ is proportional to this row particle minus row solvent square. So then that so if you can able to see that here, you can see if row solvent, low core, row cell, everything is visible here. But if you have a row solvent equal to row core, only cell you can able to visible here. This cell and core is matching. So in case to see the core structure, your solvent, row solvent equal to row cell. That means by making the visible to invisible, or you can able to identify, you can able to measure a core cell structure using small angle Newton scattering, which is that will give you, both the information being a complementary technique. The core and cells, both structure can be able to find out using both X-ray and small angle Newton scattering. So you can see in case of a contrast mismatch, you want to point what is the concentration where my contrast mismatching takes place. If I take D2O and water, so row of A, B, two component, so X into row D2O by 1 minus X into row water. So if you see the experimentally, you can see, so that what is the scattering intensity, that with Q vector we vary, and then we see in the particular that row SI, this is silicon of 3.8 10, so it's almost going to the here. So that is this contrast is 0. So this contrast matching point about 62% that we are able to see here. You can vary the concentration of water in D2O, and this is a silica nanoparticle that we measure using this silica nanoparticle, and you're able to see that experimentally what is the point where it is, contrast mismatch one can able to find out, and then you can able to find out the different information like shape and size that I will discuss little later. So if you see that IQ, that in case of, as I discussed, that the rho, some rho sample, my rho particle minus rho matrix, that's nothing but delta P. So this IQ is proportional to del rho. So in case of X-ray scattering, there it was scattering length. In case of neutron, in X-ray it was electron density. So that scattering length and rho can be determined here, contrast Ne by M. So number of this electron that there Ne by mass into D. So density of the material, then you will be able to find out the rho of the water. Here, for example, I have seen if you take water, then this will be around 0.55. So if you want to see this structure, so there you can see the rho particle is not equal to rho matrix. You can able to see this structure as well as outside structure. So if you del rho is not equal to 0, so able to see that information. If del rho equal to 0 inside the outer side, so only that red portion is able to see. So contrast is caused by molecules composed of different atoms, like hydrocarbons in water, like hydrocarbon, that Z value or that component different atom is different from that of water. And since same molecule but different densities like crystalline, amorphous regions, so they can have a different contrast. So by using this type of approach, you can able to find out the information about the core cell structures. So the most information that you will able to extract from a small angle neutron or small angle X-ray scattering, that is number density and volume fraction, like IQ equal to NV square rho P minus rho matrix whole square PQ SQ. Then this that PQ form factor and SQ intraparticle structure factor, that depends on. So from PQ you will able to get the shape and size information, shape, size and size distribution. All those three information able to get from PQ, but from SQ, that intraparticle interaction decided by the interaction between particle, that will give intraparticle interaction as well as ordering the structures. But in addition to that, by measuring the scattering length, density, volume, so you are able to also find out the composition of the material. So if you suitably vary this, decide this contrast factor, you can able to get all these information, where PQ and SQ are the two main things that PQ will give shape and size, or SQ will give you intraparticle interactions. So you can see, like if a dilute system and a concentrated system, this interparticle or intraparticle interaction, especially intraparticle interaction, that is this PQ factor, intraparticle interaction. So that will be, varies. So if you see a dilute system, the distance here R13, R23 or R12, that is much higher than that the wavelength of the lambda huge, and then the particle size, shape causes the form factor. So IQ is mainly proportional to the concentration, and it increases linearly with the particle number. And if you see a dense particle, so distance between the particle is equivalent to the size, the wavelength of the light, wavelength of the neutron or X-ray huge. So lambda, so interparticle interaction causes structure factor here. So because of the interparticle interaction, you will get a structure factor SQ in this system. So that means you can see a particle and the other lattice, and you put all these peaks. So the structure factor SQ will be summation of this. So dense system, that interparticle interaction causes structure factor, that is nothing but SQ. So that means the scattering intensity mainly depends on PQ and SQ. That PQ will give you shape and size, whereas SQ will give you interparticle interaction among the particle. That if you do from IQ plot, if you extend, this is the IQ versus Q plot, and that is nothing but PQ SQ plot. If you see here, so the combination of these two, so in the SQ you'll be able to get a peak type, this type of peak, where IQ intensity will decay like this. That means a dilute system, so mainly if a very dilute system, then you have only that PQ will be dominated. So in the dilute system, you'll see the PQ structure, where here the various things consider system that SQ, this peak will come into picture, you will be able to see this peak information. So that means by varying the concentration of the particle in a solution, you can able to get both the shape, size, and interparticle interaction information. That means if you plot that intensity of that log PQ versus Q, form factor PQ with Q, then you plot it like this. So you have a this type of plot you will get, and higher there you will get some oscillation here, high Q side. So if you see, it is going straight like this, and then it's Q is proportional to Q to the power minus 0. That is mostly, and that Q to the power is a spherical particle, then Q to the power minus 1, you will able to get a rod shaped particle, Q to the power minus 2, the low Q region, you will be able to get a cylindrical things. So you can measure the size in this region, and then PQ equal to this in this equation, whereas shape information you can also able to get by fitting this, whether Q to the power fitting to 0, minus 1, or minus 2. If you go to large Q region, you can also get the surface per volume information, which is mostly that polar equation that you will use here. You will get all those information. So if you can see here, these are the experimental data that I got from our Newton scattering facility. So here PQ versus Q, if you see the spherical particle is here Q to the power almost minus 0 here. So here, but where in case of rod like is Q to the power minus 1. Various you can see, you can feed this region, then able to see whether it's pure shaped, rod shaped, or the Q to the power minus 2, the cylindrical rod-like shape, or the elliptical space, that they are also fit by 0. So, but you have a major and minor axis here. So all those information we are able to get. And another information that we used to get from here is a pair correlation on a function. So that is probability if you have a whole scattering length of the material or the molecule is such a big, is the D maximum scattering length is possible, and there the probability of finding this small r vector, that is finding a vector of length r, the probability of finding this r vector in the whole scattering length, that is called pair distribution function. It's nothing but inverse Fourier transform of the scattering function to the real space. Like this is the intensity versus here size. If you see the intensity is decaying like this, and you go for a Fourier transformation, and you'll able to get that PR function, that is a pair distribution function. And this from the pair distribution function, that provides the real space interpretation of IQ, that is intensity. From there, you can also able to see that whether particle is spherical, rod, or core shell information, or dumbbell. You can able to see. You can see here if it is highly symmetrical. You can see here is a pair distribution function, that it is probability of finding the particular R in that whole scattering length, where vector R in the whole unit of the scattering length. If it is symmetric, highly symmetric, single cube type, equilibrium spherical. If it is you can see for cylindrical, or you can see this peak is like is following a log normal type of curve. It's a dumbbell. You can see pink one, the two peak you are able to getting here, whereas in the core cell structure you are able to get this type of image. So depending upon that, you can able to predict how the information of the shape of the particle by using this PR function. And that PR function is nothing, the probability of finding this scattering vector R, the whole scattering length. So that you can particular unit you can choose, and then you can measure, you can find out that. But you need to interpretation of this result is quite difficult. So you need a very good model to fit this. So you have to select a model first, the possible structure for the interaction, and then you have to fit into experimental parameters, and then change whether it's good fit, then you will able to get the complementary result. If it's not fit, it's not perfect, then again change the model, and by changing this way you can able to find out better fitting, and from the fitting how you will able to get that characterization part, that we'll discuss after 2 to 3 minutes. Thanks. So whatever so far we discussed about the principle and the instrumentation part of small angle scattering and how you can analyze those data. So, but analysis part of the small angle X-ray scattering or neutron scattering is quite difficult. It all depends upon your fitting model. So if you choose a better model, if you have first you have to gain an idea about whether you have a core cell particle or you have a spherical, elongated, whatever structure by some other technique. If you identify and based on that knowledge, you can choose a good model to fit. So first you have to select a model for the possible structure and interaction, then fit the experimental data using selected model. So you have to fix the value of known physical parameter as many as possible, and then you see whether you have got a good fitting or not. If it is a good fitting, so this could be a possible model. So then you can by slight modification in the model, all those things you can be able to get the final model, and the result you will get you will get the results. But if your fitting is not good, then you have to come back again and you have to change the model to fit in some other model to find out those parameters. Like you shape, size, or different informations. Like one example I have given here, that how the effect of temperature changes, surfactant structures, and that could be measured by using, small angle scattering facilities. So if you take a P85, that is a Pollock-Jammer 85, is a block copolymer. It is EO ethylene oxide and polyethylene oxide, and ethylene oxide, like you have a PP. This is a block copolymers. In that block copolymers, it forms different structure depending upon the temperature. If you take a 30 degrees centigrade, that 30 degrees centigrade, you can see there here it is mostly is unilamellar. So that's the micelles are exist here. Once you go to 50 degrees centigrade, they form some unimers are there in case of 30 degrees centigrade, like individual, like these surfactants are there. As you know, the surfactants have a, it's a head group and tail group. This is head is hydrophobic and the tail is hydrophilic head group and hydrophobic tail group. So that structure you will able to see only in case of my unimer, that is at 30 degrees centigrade. When you go to 50 degrees centigrade, some of the unimer convert to micelles. So you have a mixture of unimer and micelle here. Whereas if you go to 75 degrees centigrade, you will able to see that rod-like micelle structures. So those information, if you go do the small angle neutron scattering, and then you fit here, this will be q to the power -1, is q to the power here 0, here 0. That's this unimer or micelles there. So those information you will be able to get by fitting with this model. And the low scattering at low temperature is from block copolymer, mostly dissolved state here uniform. But when the scattering intensity will increase with increasing temperature, so that the scattering intensity is where the scattering intensity goes to here. So here is spherical micelles are blocking forming here. Once the micelles are formed, the structure of the function as a temperature and is further increasing. These micelles, they join and grow in a rod-like feature like here. So based on the temperature, how the transition occurs in a micelles. So those information by simple by in small neutron scattering data, you can able to interpret just by fitting this. How the decay of how the scattering intensity varies with Q. So you can able to get the information. So this is another example that you have a surfactant that is a micelle structure, but it says a the SDS, like is a DTAF or a C12 ethane, like mixed micelles. So you can able to find out whether when it's forming a elliptical structure, you have a major axis, minor axis. So by fitting the model with whatever the data you are getting here, and to that data you fit your model, and then you will able to get all these this major axis, minor axis, as well as polydispersity index. This here is 15% is the polydispersity. So all these information you can able to get from the small angle neutron or X-ray scattering. So you can see here you have a ferrofluid of Fe3O4 nanoparticles. So that is, you can see this is a core Fe3O4 nanoparticle. On that there is a bilayer of surfactant. One layer is this and one layer is this. So you have a bilayer structure. So those information that you have from DLS, you know, overall size, that DLS will give you the whole size, so that you will able to measure hydrodynamic diameter. So that is about 10 nanometer by dynamic light scattering, dynamic light scattering, that is DLS, that is used for, you know, hydrodynamic diameter size measurement. But that you can complement that data with the SACS and SAN study. If you go for a SACS study, the small and X-ray study, so you will get only the information from the electron cloud of the Fe3O4 nanoparticle. So that core information will get only the core size. So you'll get about 4.8 nanometer will be able to get from the SACS study. But if you go for the SAN study, what you will get the particle size, especially the thickness, that bilayer structure here. So those bilayer structure information, so this to this region, so you'll able to see that core as well as cell structure, that your core is 4.8 nanometer, cell is 4 nanometer, and these two technique added up, you can able to get that it matches almost that of the size obtained by the DLS study. So by the normal light scattering study, you are able to get the whole information by you, but with the combination of SACS and SANS, you can able to get the information of the core cell structure by using, you know, scattering techniques. So another example I have given here, you have a CTAC molecule, that is cetyl trimethyl ammonium chloride, or cetyl trimethyl ammonium bromide, CTAB or CTAG. If you will take, this is ammonium chloride and this is ammonium bromide. Here is chlorine and here is bromine. Since bromine is a bigger atom, the high jet material. So if you go for a comparison between SANS and SACS study, if you see, you can see in case of SANS, you are getting information about that only this peak, a single peak you are getting. That is the SQ factor you are getting. But if you see the SACS data, you are getting a, you know, there is a hump here. So you are able to get a hump here. So that hump you can see here. So that, and if you go to bromine is being a high jet material, that when you go for a SAN study, you can see in the SAN study you are getting a single peak like that of CTAG, but when you have a bromine, in case of small angle X-ray scattering, because bromine is high jet material, you can see this is the small peak where here the shoulder, that you are getting, instead of that you are getting two prominent peak in case of, you know, SAC study. So that way you can able to identify the surfactant molecule also by using, you know, the SAN signal that can assess the contrast between the solvent and the hydrocarbon chain of the core molecule. That a CTAG molecule is there, that hydrophobic chain of that will give the SANS data. Here we give, and the SACS is sensitive to the inner structure, that core, that you have a that head group here, and then you have a this bromine atom is there. So because of that high jet bromine, so what will happen, that because of the electron density of the head group, the counter ion and penetrate the, so because of that you'll able to get that information of the SAT. So you have a bromine type of atom here in the head group, and you have a tail here, and in the other one you have a chlorine atom. So depending upon the Z value, so Z value will able to identify both the information. So the contrast variation obtained by SANS and SACS prove the difference between the nucleus of the atom and electron density respectively. So that way you can able to find out the information about the structure. So, but the important thing is for getting a neutron experiment study, you need a nuclear facility. So because the neutron source, you need a neutron source that need a nuclear facility. So if you see the nuclear facility at VRC, that is in Dhruva reactor with this vertical tank type reactor of maximum 100 megawatt, and huge natural uranium metal as a fuel. And here in this, whatever the beam line we have separated out, which called collecting, and then if you see that you have a sample here on the sample surface here, then that from the guided that beam line is coming and it's passing the neutron beam and falling on the sample is here, and then you have a beam stopper. This is the beam stopper beam stopper, so to prevent the burnout of the detector. And here is the sample, and whatever the scattering is there, that scattering measured by the detector. So here we mainly use the monochromatic velocity selector, and then the wavelength is either 4 to 10 angstrom. So that Q range that we measure is about 0.015 to 0.5 angstrom. So anyone from outside base, if they want to do this neutron beam, they can also use this neutron beam facility. They can write to the person, to the authority of that nuclear facility of that small angle neutron studies, or neutron diffraction study, or scattering or diffraction, so they can help you for all these measurements. But the important thing is that by using both small angle neutron and X-ray scattering, giving a complementary technique, you can able to get better information by using this type of techniques. So that we studied so far, that initially with X-ray diffraction techniques. So how the X-ray and this uses for different scattering as well as the diffraction. The Bragg's law satisfied. Then you have the diffraction that uses mainly X-ray diffraction. We discussed with the single crystal XRD, synchrotron XRD, then grating angle XRD. All those XRD techniques we have studied and discussed. Then we have discussed that X-ray absorption spectroscopy, that X-ray absorption fine spectra, how EXAFS, that is Exynos and extended EXAFS, that both will give you coordination at number as well as oxidation state. But from the XRD, you can able to find out that crystal structure, phase formation, like the strain, stress, all those information we discussed. And then also using extrafluorescence, how you can use for element analysis. So all those things we discussed. Then neutron diffraction, we can employ it to use the information about both the nuclear as well as magnetic information by using neutron diffraction techniques. So in addition, that how the scattering techniques can be used, especially small angle X-ray scattering or small angle neutron scattering, to identify the shape, size, as well as structure, and what this surface characteristic of a material. So this so far I have covered mainly diffraction and scattering techniques. So next we will go to the optical and electron microscopy. So all those techniques, earlier techniques, were based on scattering and diffraction. Now it is about optical or electron microscopy. So if you want to see the structure or the surface of a morphology of a material, you have to go for an optical or electron microscope, depending upon the size of nanoparticle, size of the particle that you are looking. If a size in the visible region, or in the larger size, the micron size is like 20 micron, 50 micron, you can able to see using optical microscope. But if your size is nanometer range, like 200, 300 nanometer, and that range, you have to use for a electron microscopes. So if you see that is scale and microscopic technique, so as I discussed, that XRD mainly cover the structure determination, that crystal structure information, those things you can able to see in the atomic microscopic properties. But if you for applied research, so there you need the component analysis, the fracture mechanics, microstructure, how the porous structure are there in the material, and what is the shape, size, and information that we would more visually want to see. So for that, you have to go to optical microscope, as well as SEM, scanning electron microscope, and transmission electron microscopes. So the structure that determines the properties. So mainly you have to identify the structure by using this microscopic technique. If you see the microscope, that some basics of the microscope, that came from a Greek word that is called micron, that means small, and scopus, that means to look. So it means to combine is to see the small molecules or small entities. We use microscope. It is an instrument that views objects that are too small and the science of evaluating or investigating the small object is called instrument that we use is called microscopy. So the microscopes can be divided into two parts mainly: a simple microscope and a compound microscope. And This compound microscope is mostly light microscope where you use like phase contrast microscope, like normal optical microscope, depending upon the phases that you can identify. Then you have a fluorescent microscope or bright field, dark field microscope you can use. That all is that light microscope that you use. But if you go to the another type of compound microscope, that is electron microscope, where that we will mainly discuss in the next class, that is scanning electron microscope, transmission electron microscope, and confocal electron microscope. And see that the terms and used in microscope mostly you must be heard that magnification one, that how the degree of enlargement of the that you can how the small object can look how big, that there's nothing but degree of enlargement, that's magnification. It depends upon the focal length of the objectives, magnifying power of the eyepiece, and you have a resolution, like if a two object is there, the ability to resolve the two adjacent structure. That means you have a one object is here, another object is near here. So to identify that interface, that ability to resolve to these two images, if you see one is in this way, that will be the nothing but you can change the resolution and it can be resolve this two structure. And you have a limit of resolution, that is nothing but that minimum distance between two visible objects which can be separated and or not connect to each other. And then you have mostly you have a numerical aperture, that Na equal to n sine theta by 2, where n is refractive index, theta is the angle aperture, the ratio of diameter of the lens of the diameter of the lenses to its focal length that uses, and you have a working distance, how far your substrate to the the lens is kept, that eyepiece, lenses are kept here. So that distance, depending upon this distance, you can able to varying the working distance, you can able to better image you can create. So if you see a conventional lens microscope, mostly use an objective lens here, and then you have a convex or convex lens, and finally by passing through this focal length, you're able to get a image here. So you can see that normal formula that we all know, that 1 by u, that object distance at v is the image distance equal to 1 by f, that focal. So magnification here, v by u, distance from the object, that this image from the lens to the distance from the object. You can see here that you can see a opposite, that inverted image you'll able to see in a conventional microscope. You can see here, if a microscope, that is a scanning photography, you can able to see this type of direct image. In photography also you can see, but if you go to microscope, that we get an inverted image. So from resolution wise, you can increase the better image. So but in optical microscope, in comparison to the lenses system, with the optical microscope, that uses mainly 4 components. One, you have a illumination systems, that is that radiation source. Like in case of electron microscope, we use tungsten filament, but here the radiation sources of some UV or visible light, that we use here, illumination system. And then you have a sample stage. You can see here, this is the sample stage, where you can see a conventional optical microscope. You have a eyepiece here and the lenses are here. You can see the sample you can kept here. You can able to see the images from here. And then you have an imaging system. This is the imaging system that is there. So there are objective lens to focus the beam, so the beam can be focused, and then you have a projector. There you will get a like this type of image. You will able to get an imaging recording system that convert radiation into different parameters. You can see the light source on the top of the lamp is here. Either it's a UV or it's a visible lamp, and then you have a condenser lens and specimen is here, the tissues or some sample, then it passes to object, eyepiece, and finally you'll able to get a image on the projector. So this is the outline of a optical microscope. When you can see the better quality image, to often you have to go for polishing, because on the top surface, rough surface, it will finely polish, especially the metallurgical sample. You have to ultra polish by mirror finish to see the structures. You can see these are some brass molecule, brass in which you can see the inclusions are there, that those things you can able to see after etching. It's stainless steel, and this is a deformed niobium, how the niobium which distributed those images you can see. By etching, you can reveal that top surface can etch out by chemical, different chemical you can use and to remove the top surface material of the surface, and you're able to see the underground that most of the images, surface morphology. You can see here the bronze revealing a karst dendritic structure. This is the bronze after you can see how this dendritic-like structure is grown and grown on a substrate, how this algae or they are growing on this substrate, those information, or aluminum silicon alloy by the grades that is precipitation or something. So those information you can get at the micron scale, that is micron scale, like about 20 micron, 30 micron, that scale zone, you can be able to see using the optical microscope. But if you want to see small object, it's not possible by using the optical microscope. For that you need the electron microscope, because the electron has a the optical microscope wavelength is mostly in the if a visible is 400 to 800 nanometer, or UV you can take 200 to 400 nanometer, but that wavelength is quite high. But if you go to electron microscope, the wavelength that we are using is much smaller than the visible light, and that allows the electron microscope to produce high resolution image. Where the wavelength is small, so the wavelength, if you see here, this for a wavelength for electron, it's 0.0022 to 0.1 nanometer. If you take SEM, it is about you use 30 kV, that's corresponding about 0.2 to 0.1 nanometer, whereas in electron transmission electron microscope, which is 200 kV, that is about 0.0025 or so nanometer. So wavelength is very, very less. So because of that, you need an electron microscope. The electron microscope are more useful to get image at very smaller object. So, and then this electron have strongest interaction in comparison to optical, that light, that is the electron, they have strongest interaction with the nature of any radiation, so many type of information you'll be able to get. And there's high intensity. The intensity, if you see the fluxes, that is very high. It's really high energy beams of electrons are relatively easy to generate. You can use a thermalic emission where high energy electron beam can be generated by using different magnets, like magnetic lenses, that the acceleration speed of the electron can be attained, so you'll get highly energetic. So it is used in conjugation with variety of ancillary techniques, like in case of thin sectioning, like immunolabeling, negative staining. So those can also be combined with this technique in conjunction with this electron microscope. We'll be able to get more clarity image. So if you see the whole electron microscope, if we go to the scanning electron microscope or transmission electron microscope, that depends upon the interaction of the electron with the material. So this image I have already discussed. So this is the electron beam is coming on the sample, and you have a sample here. Then electron beam will interact with this material with a specific volume. So that is called interaction volume or electron range, up to which the electron beam can be propagated. And then once the electron beam falling on here, so then there is many type of interaction takes place. So the one possibility that is that the incident electron can interact with the material, and it can be returned back. That electron is called like backscatter electron. And another way, this electron can be absorbed inside this, or it can be scattered. It can be excited. It can remove another electron. So that will be a secondary electron. You can see here the secondary electrons. So these two, backscatter electron and secondary electron, they are used in scanning electron microscopy. So if you see here, the backscatter electron is coming little lower from the substrate, inside the substrate of the sample, whereas the second electron coming from the top surface. So being it's coming from the inside, that backscatter electron, that will bring more information about the inside element. So that backscatter electron mostly used for for EDAX, that the analysis or element analysis that using the redox facility of SCM, or the secondary electron you can use mostly for, commonly used for, surface topography. It's coming from the top of surface. And when these two phenomena, along with this phenomena, there is possibilities of X-ray generation, like when this electron comes, that as you know, the electron is, the core electron is here, then this electron beam is falling here or something. So this electron can come out, because of that, so higher electron that can be jumped to this position. What are the excess energy here? That can be emitted as X-ray fluorescence or some other X-rays. So what you will see, so those X-rays can be used for SEM or EDAX mapping or TM, EDAX mapping, energy dispersive spectroscopy, where that you can use that wavelength wise, or you can use energy wise, you can sort them, and you can use them for chemical composition analysis. For example, if you have a zinc oxide sample, you can able to get zinc K alpha, oxygen K alpha, and you can identify their percentage also by using this X-ray EDAX facility. In addition to that X-ray, they can also generate OJ electron that we'll discuss. This OJ electron is a 3-electron process. That means one electron is coming, one leaving out. This electron falls here. Again, it creates a hole here. So that will be followed by a 3rd electron here. So here the excess energy release, that electron will be released here. So that will be the OJ electron, knockout electron. So that OJ electron is 3-electron process in OJ electron. So that we will discuss when you go for the OJ electron spectroscopy. So that OJ electron can be used for, for OJ electron spectroscopy study, where you can use them to identify the morphology as well as, oxidation state or surface characteristic that you get in addition to the X-ray photoelectron spectroscopy. That the electron here coming with that electron also used as a X-ray photoelectron spectroscopy, because the photoelectric effect this electron can be observed, and the knockout electron can be used as a X-ray photoelectron spectroscopy. And in addition to that, we have also cathodoluminescence. Some emission is possible. You can use them for luminescence studies. You can able to get some luminescence characteristic using this. In addition to the electron beam scattering back or the top morphology by using scanning electron microscopy. So some of the electron they can transmit through the system if you have that particle size is small, that it's a transmission of about 90 angstrom or so. So what will happen that electron will call as a transmitted electron, and this transmitted electron that will utilize in case of transmission electron microscopy. TM utilize that electron, and we used to measure that particle size or electron diffraction pattern, or even use that chemical analysis by using EDAX facility of TM. So here, 2 types of transmission electron is possible. One is elastically scattering, another is unelastically scattering. Another is unscattered, that will direct transmitted. So with elastically scattering, that means here there is no transform of change of energy. So if you are inelastic, so there is a change in energy of the incident electron and the electron after transmitting to the material. So that because of this inelastic interaction, so what will happen? Some energy will be lost. So from that we have a electron energy loss spectroscopy, yield spectroscopy, that is from this part of this transmission electron microscopy. So that yields an electron energy loss spectroscopy that you can utilize to find out the 2 information from there. One like Xness, like one here is illness, and like electron loss extended spectroscopy is something that. So those illness, that is near edge and extended edge, that is extended spectrum. So both those, one will give you oxidation state, and both oxidation state and coordination number can be found out, like the absorption, Xness, you can use your illness and let's say extended absorption technique here in case of electron energy loss spectroscopy, you can able to find out oxidation state and coordination number. So we'll discuss all those things in case of scanning electron microscopy study and transmitted microscopy study, as well as XPS or photo this OJ electron spectroscopy. So far today, in today's lecture, what we covered that small angle scattering studies. That's mainly two things. One is small angle neutron scattering, another is small angle X-ray scatterings. So these two we have discussed, and these two techniques are complementary to each other. So the small angle X-ray provides information about the mesoscopic length scale, that is 1 to 100 nanometer. If you see here, this region, that is here, that wide angle X-ray diffraction study, that gives interatomic structures. Mostly it can, here that web vector Q is quite large, so your theta is here, theta is greater than 10 degree here, 2 theta is 10 degree here. So, but angle is here. But if you see that the small angle, this is scattering. So here theta, that is less than, this is less than 10 degree. So 0.1 to 10 degree in that case here. So by going to the small 2 theta value, you can able to see the structure of a mesoscopic length scale of the particle. That means you can see the structure of nanoparticle, protein, so size of the protein, size of nanoparticle, as well as different surfactant, how the vesicles, micelle, those information you can able to get. And such data analysis is application dependent and using a diverse set of approximation and model. Like electron microscopic technique, that what you see the particle size, that's directly you'll able to get. But in case of small angle X-ray, neutron scattering, the data will often, those are, we had to interpret it using diverse set of approximation as well as models. And neutron, they are complementary to each other. So because of that, you will get better information, like the core cell structure, where some X-ray can give the core morphology of the bone structure, you can say, and neutron can give the leaf structure, the outside tissue, those structure. So whole imaging, whole thing structure you can able to find out using these things. And whole that neutron and X-ray small scattering technique depends upon the contrast properties, that is rho of density, rho of sample minus rho of solvent, rho of this is solvent, and rho of sample, that these two difference. So that you can able to use, depending upon the variation in the contrast, you'll able to see, making invisible to visible, you can able to identify the structure. And then you have a model to fit, and depending upon the q to the power 0, q to the minus 1, minus 2, you can able to get the shape information, as well as you can also get from the size, that using PQSQ form, can able to get the shape, size, as well as dynamic structure from there. And then we studied about a little bit about basics of microscopy, how the optical microscopy can use to identify, to see the structure of a micron size, like more than something like 10 to 20, beyond higher size nanometer than the micron scale. But in case of smaller nanoparticle, smaller the object, to see that you need an electron microscopic technique. And because that electron is very, very low, that uses wavelength is very, very low. That's why you can able to see a very small object by using the microscopic technique. And this microscopic technique, that using different type of electron interaction, how the backscatter and the secondary electron, as well as transmitted electron, or the X-ray is emitting, or other electron emitting. So those can be utilized in different techniques to identify the different characteristic of the material. We'll discuss the next two class. So the next class mainly will be I will discuss on scanning electron microscope and transmission electron microscopes. If there is any question, you can raise on the chat box, or you can also mail me. Okay, if there is no question, then we will conclude the class, today's class here. So we'll meet on Friday for discussion on electron microscope, especially on scanning electron and transmission electron microscope.